Hey everyone, welcome to The Explainer. Today, we're setting the stage for a really deep dive into the hidden logic that controls massive industrial automation systems. Look, if you've ever stared at a towering chemical plant or, a sprawling manufacturing facility and wondered exactly how thousands of valves, pumps, and motors know absolutely what to do and when to do it, well, you're in the right place. We're going to completely unpack the absolute foundational rules of control and command within somatic PCS7. Because it really all starts with this one fundamental tension. In a massive facility, who actually holds the authority to act? Is it the human operator sitting in a control room clicking a mouse? Or is it the autonomous code running silently in the background? You see, the entire architecture of process automation revolves around this constant, delicate negotiation for control. Misconfigure this, and the whole thing grinds to a halt. Engineer it perfectly, your entire facility runs like a symphony.
Okay, let's dive right into this. Here's our roadmap to make sense of it all. First, defining system authority. Second, buttons versus switches. Third, routing the control signal. Fourth, mastering the tank farm. And finally, the ultimate command pathway.
All right, part one, defining system authority, the master gatekeeper. To really wrap our heads around this system, we actually need to shrink our focus down to the absolute smallest unit of control, a single decision point. And before we get tangled up in complex wiring diagrams, let's define one absolutely crucial piece of jargon, modliop. Seriously, think of modliop as the master gatekeeper input variable for literally any block in the system. It's a strict binary choice. A value of 0 grants authority to the human operator. A value of 1 hands over that authority to the system logic, meaning the program itself. There's no middle ground here. Now, what's really interesting about this slide is seeing how that core tension actually plays out. Take a look at the top left quadrant. When modliop equals 0, you're traveling down that orange pathway. The human has authority, firing off commands via an operating system faceplate on a screen. But drop down to the bottom right. When modliop equals 1, boom, you're in the blue pathway. The logic completely takes over. And notice those giant padlocks in the other quadrants? Yeah, if a human tries to force an automatic command while holding manual authority, or if the code tries to run while the human has it locked out, access is outright denied. A mismatch means 0 action.
Moving on to section 2, buttons versus switches, the mechanism of command.
So once the master gatekeeper has assigned authority, specifically when it hands the keys over to the code, how does the system actually interpret the signals coming in? Well, that brings us to our second vital parameter, feature bit 4. Honestly, I like to think of it as the translator. It dictates the exact physical interaction paradigm we're using. Basically, are we dealing with momentary button presses, or are we looking at permanent, hard-toggled switches? To grasp why this distinction is so crucial, let's quickly contrast these two physical realities. A momentary pulse requires just a single, temporary signal spike to change states. You tap it, it triggers, you're done. But a persistent, continuous state? That requires a constant high or low signal to maintain its status. If that signal drops, the state changes immediately. Let's look at exactly how feature.bit4 handles this. On the left side, if feature.bit4 is set to 0, we are in button mode. The system is just waiting for a temporary pulse, a quick spike from 0 to 1 and back, just to kick on automatic mode. But on the right, if feature.bit4 is 1, we're in switch mode. The system now relies on a persistent signal. And what's absolutely vital to remember here is that in switch mode, a high signal, a 1, means automatic. If it drops to 0, it means manual. Because of this dynamic, the dedicated manual input, man-mod-lie, is literally completely ignored by the system. The switch's position tells the whole story. All right, section 3, routing the control signal, the action pathway. Okay, now that we understand who actually has authority and exactly how those signals are translated, let's follow a single, solitary command. Notice that physical switch mechanism right in the center? This represents the internal logic evaluating all the conditions we literally just talked about. Depending on whether the state is set to automatic or manual, this internal switch toggles up or down. If it toggles up to the blue line, it successfully connects the code's open or close commands straight to the final output driver. If it toggles down to the orange line, the operator's commands get a direct physical path to that exact same output driver, moving the actual real-world valve. But there's this brilliant safety feature built right into the architecture. I really want to highlight the crucial architectural note on the right side here. When you're in manual mode, the commands open man and close man are sent directly from the screen faceplate to the block. But by default, These inputs are completely invisible on the continuous function chart, which is the engineering canvas. Why do that? Because they are designed exclusively for the operator interface. Hiding them ensures a programmer doesn't accidentally wire a piece of logic into the manual override, which, trust me, could cause a massively dangerous, unpredictable overwrite during a critical live procedure.
Section 4. Mastering the tank farm cascading automation.
So we've totally mastered the micro rules of a single valve. Now let's zoom out and apply these strict rules to a macro, real-world scenario. Imagine you're running this facility. You've got multiple massive material tanks with all these interconnected valves and pumps. Clicking individual valves on a screen one by one just to transfer material, that's wildly inefficient and practically begging for human error. We need to engineer a central switchover mechanism to toggle all the pumps and drives simultaneously. But remember our rules. The absolute critical prerequisite here is that feature bit 4 must be set to 1, switch mode, across all those different drives and valves before we can even think about routing master commands. To solve this beautifully, engineers use a fan-out topology. Essentially, you create a master switch, an OPT03 block, that captures the human's single selection and translates it into hard logic. Those signals then feed into distribution hubs, which you can see right here as OR04 blocks. Look at how a single line goes in and then just branches out across the entire facility. With literally one click, the operator can flip the ModLiOp gatekeeper variable for every single tank, valve, and pump instantly, granting localized authority to the code for the entire tank farm in a flash. Let's see how this builds into actual motion. Once the system has that authority, automation executes in 4 exact steps. Number 1, a trigger event happens at a dosing tank. 2, a relay block transmits that signal. 3, a chain reaction instantly opens the downstream material tank valve. And 4, a pump start command activates the drive to push the fluid. And this diagram brilliantly illustrates that exact chain reaction in visual form. Just follow that blue line of programmatic logic. Because we properly configured the master gatekeeper and the translator parameters across the whole plant, a single human action on the far left, just opening one dosing valve, creates a signal that flows uninterrupted through the relay, automatically opening the material tank valve and subsequently spinning up the pump. Guys, this is exactly how one human click safely automates an entire facility. Which brings us to Section 5, the ultimate command pathway, synthesis and truths. All right, let's bring all the pieces of this puzzle together and shatter some of the most common misconceptions operators face out in the field. If you are ever troubleshooting a system, you're going to want to lock this diagnostic matrix right into your mental model. Let's do a rapid-fire myth versus fact. Myth: the operator can always override the system. Fact: absolute authority strictly requires ModLiOp to equal 0. If logic holds it at 1, you are totally locked out. Myth: you always need both automatic and manual signals wired up to control the mode. Fact: as we just saw, in switch mode, the manual signal is completely ignored. Myth: feature.bit4 is just some visual setting to hide unneeded pins. Fact: no way. Feature.bit4 determines the fundamental logic of how signals are read. Manual pins are hidden independently for operator safety. So the crucial point is this: there's really no magic happening behind the screen here. Every single signal, every interaction, and every choice boils down to one incredibly strict, beautifully designed hierarchy. Let's trace it one last time on this ultimate command pathway diagram. Start right at the top. ModLiOp decides the path. If it's 0, we go left. Pure manual control, straight down to the output. If it's 1, we jump to the right, where feature.bit4 evaluates whether we're listening for a button pulse or a permanent switch. That then dictates the automatic mode, which allows the program's commands to flow right down to that exact same final output. It's just a flawless, closed-loop orchestration. And because this architecture is so strictly reliant on standardized logic rather than just hardwired physical buttons, it allows for some incredible future-proofing. Engineers can use something called textual interconnections. Notice how they can write logic on the left side of the screen that routes to hardware on the right side of the screen that literally hasn't even been built, installed, or compiled yet. The system just patiently waits for the hardware to exist, knowing the foundational logic is already perfect. Which leaves us with a pretty incredible thought to close on. If the strict rules of ModLiOp and feature.bit4 allow us to safely build logical bridges to hardware that doesn't even exist yet, what actually limits the scale of tomorrow's automated worlds? The answer isn't the software. It's simply how big we dare to build. Thanks for joining me on this explainer. I really hope this completely changed how you view the hidden logic of automation.